Hello and welcome to podcast number 20. Been away for a couple of weeks. Part of it was a trip that started on the weekend, and when I returned, well, actually during that trip, everybody got sick. So we had a bit of a cold going on, and I didn't want to be on here, still clearing up a little bit from the throat. Didn't want to try to do a podcast while I was hacking and coughing. Did do a couple of podcast interviews, meaning that I was interviewed on a podcast, including one on uptime, on the application of AI and machine learning in our industry. That kind of thing. This one I'm trying to get out so we say, like I said, excuse me, so I can get out the next newsletter. And as promised, we're going to include just a couple of snapshots showing you the how electrical signature analysis and vibration kind of match up a little bit. So this comes along with the study we're doing and the paper that we're working on at the moment for the Vibration Institute on that energy relationship, where it works, where it doesn't work, and why. And then part of that is also how much energy can be gathered by the transducer and so on, and what relates to actual, the kinetic energy of the motor itself versus the surrounding structure. So we included motion amplification as part of that. So you can see here on the screen, we have one of the test motors, and we'll go ahead and pop up the data. I'm going to have to pause it because, as we've talked about before, this just eats up a lot of memory. In this first example, looking at our low frequency spectra, so we're going to use DMOD to kind of evaluate it because of the fact that we're going to have here mirrored on either side, we're going to have the same signature. But you can see the running speed, a little bit of a pole pass frequency. If you look here, you see the pole pass frequency lines up. That means casting void. So is that urgent or destructive? No. In the long run, it'll have an effect on the bearing and so on, but really you balance that stuff out. That's an electrical unbalance of a sort. So you see a small oscillation in the current. So let's go ahead and take a look. We're going to pull up the channels associated with vibration, and we're going to leave open this DMOD spectra. You can see it's taking a few seconds again. The software we're using to do the screen capture just takes up a lot of memory. So I'm going to pause it again until this pops up. So here we go. Primarily running speed, and you can see just under 60 hertz here. Here's some smaller stuff. Let's go ahead and pull that up as harmonic cursors. So you can see that I've got, there's line frequency there, but I've got small peaks, all the way up as not unexpected. Same thing here in the running speed here. That is about, 0.38 amps at 1789.5 RPM. So that's the actual running speed. Now I took these concurrently, so it's 48 seconds of vibration data. At a high resolution, so the bins are quite tight, as you can see. So here we go. These are both vertical. So this would be with channel 8. I've got this on the opposite drive end of the machine, and the other one is the drive end of the machine. On the vertical direction, that's 0.438 inches per second at, again, the same speed. And on the drive end, that's 0.278 inches per second at the same RPM. So you see how these match up. You can see some of the smaller peaks kind of matching up as they go up here. Now I'm going to pause again, and I'm going to go to the high frequency data set, and we're going to take a look first at current signature, and then we're going to take a look at kilowatts. Now kilowatts brings everything down to 1 time RPM again, but I'm going to do a little bit of a comparison so you can see what the peaks look like in ESA, in current signature, versus vibration in inches per second. So with that, we'll pause. So in any case, when we first take a look, you can see current spectrum, very, very different as far as vibration spectrum. You notice we're at about a 5,500 hertz rollout, but total is 360,000 CPM if I were to do it as CPM. So let's pull into an area of interest. In particular, let's see if I have... here, let's pull up power peaks, and let's take a look at static eccentricity, just so we can see where the peaks are going to be. So we can see here, it's identified where the vibration peaks would be for that. Let's zoom in. I'm hoping this goes quickly, or I'll have to pause while we're waiting. Again, Camtasia takes up a lot of memory while it's recording. So it's recording me and it's recording the screen. If I just did one or the other, it would be a lot faster. Let's go ahead and pause while we allow. Now here's a few things to notice. Okay, so right off the bat, you'll notice the running speed, which is what we had before, is at the 1789.5 RPM. It's showing up here as well, also at 5.9 RPM, or 0.5 RPM, but basically you can see its side bands around the line frequency. So this distance here would be this distance here. So it's side bands on either side, which is usually what causes a little bit of confusion for your average analyst. Now, I'm going to zoom in out here to see what we look like as far as static eccentricity. There's not much here. It's not showing up as any significant value. And again, we'll probably have to pause, but let's go ahead and zoom in. And here, as you can see with static eccentricity, we're lined up exactly with some of the peaks. It looks like if I were to go dynamic, would show up as well, and that same pattern will show up here in dynamic or static eccentricity in electrical signature analysis. You can see I've got some small peaks here, and as you can see, very, very low peaks. Now I am in inches per second. I am in velocity. So I'm going to do two things real quick. So we'll pause one more time, and I'll show you what that looks like. Now, because we're in a higher end of the vibration spectrum, and I'm using accelerometers, I've changed it back to G's, so acceleration. And as you can see, here's my peaks associated with dynamic eccentricity, and the peaks up here are virtually non-existent. They're there, but they're extremely low. So next step, we're going to take this and we'll explore a little bit where we go back to 1 time RPM for electrical signature analysis. And one of the strengths of electrical signature analysis, as a matter of fact, which is in the kilowatt analysis of a machine. How can I then look at what conditions are? Well, if I'm looking at dB down, such as in this case, everything happens in peak pairs. All the calculations are the same. So you can see vibration, I'm right in the same area. But I've got plus and minus 1, 3, and 5 times my line frequency, which is my carrier frequency. So that's a lot there. dB down allows me, regardless of load, to be able to specifically identify defects and things along those lines. Now, when I go to kilowatts, that changes. Now I'm going to be back to each thing being identical to what I would see in vibration analysis, except that I'm looking at watts and kilowatts. Well, why is that important? Well, because I can use that and compare it directly to the load of the machine and start talking in terms of, this defect is such and such a percentage of all the energy in that machine, in the air gap. So we're going to be talking about air gap kilowatts. Now, this is where things get interesting when we talk about vibration and the energy relationship with vibration. Because in kinetic energy, you're looking at the entire structure moving and all of the weights and everything else, versus air gap losses in a machine where you're talking about the directly measurable kilowatt losses at the basically the supply to the motor. So in any case, let's go ahead and pause again, and I will get that set up. Now, just to start out where we were, you can see dynamic eccentricity. Now you can see when I'm in the power spectrum or kilowatts. Remember, this is kilowatts, not if I'm doing machine learning, power spectrum is completely different. This is not the same thing. So if I come down here and I take a look, these peaks are now lined up. You notice this peak is not. Well, that's because that's actually some type of power harmonic versus this up here. Now you notice that the actual energy loss is now going to be in terms of a few watts. Okay, so 0.06 kilowatts is 60 watts, for instance. So when I'm talking about these peaks up here, down here, I'm at a much, much lower value. Say in this case 3 watts, 8 watts, and about 4 watts versus, this would be, I've got it in inches per second again, so this would be virtually 0. 0.004, 0.0004 inches per second, so extremely low versus here. So I'm going to go ahead now, and we're going to take a look at, down here at this end where we are talking in terms of a slightly higher loss. So we're talking about when we're talking forms of kilowatt losses and running speed versus the running speed or one-time RPM in this case. Let me go ahead and pause again while this is catching up. Now again, we're talking about watts here. This is about, this is going to be that pole pass frequency peak. That's at 33 watts. So that casting void that we talked about before is about 33 watts of the total load. The running speed, this would be unbalanced, or this would be strictly unbalanced. You can see here I've got very, very tiny 1 and 2 times, so this is not misalignment. Have something similar here, and then out here you can see this is line frequency and twice line frequency. Those are harmonic peaks. I will have very, very small values of those in my vibration, and that has to do with power harmonics. It's incidental in this area because the machine's running across the line. So when I take a look here again, there's that 1789.5 at 0.591, so very high unbalance. That's at the drive end. 0.9 inches per second. Now this is vertical. Now in the paper I'm working on, this is actually, when I take a look at the analysis, I believe I talked about this before, and I look at the orbit using motion amplification, you can see my vertical is extremely high. So we'll take a quick look at the horizontal next. And in both cases, you'll notice this value here doesn't change very much, and this is 114 kilowatts. I believe it averages out to about 116 kilowatts between the two, right at that RPM. Okay, so you can see that there. You can see that my peaks are lining up. They're small in vibration, but they do line up, especially that one pole pass frequency is not showing up heavily in vibration, which is very interesting. So let's go ahead, and I'm going to pause and again do a few more things here and show you one more thing from the horizontal. This is vertical. I would note while I'm setting this up, this here, just to put into perspective, this is the dB valuation of the vibration data. So you can see I can still do it in dB here as well, and it'll be relative whatever my peak is, which is going to be down here close to 0. But in any case, let's go ahead. I'm going to switch this over to linear so we can take a look at it. Now this is slightly different in that this is the horizontal reading, which it didn't have a lot of freedom of movement horizontally, but the actual base that this motor was set on is 25 horse. It's a relatively heavy machine, so the base became kind of a spring in mass. So it was moving a lot vertically. I believe it was 8 thousandths peak to peak. So in any case, let's take a look in here. You can see I have a peak that's close to my pole pass frequency. It's a little higher in inches per second here. My actual inches per second now, 0.065. So far better than where we were on the vertical reading where I am horizontally, but still on the opposite drive end, 0.3. That's because it had more freedom of movement that direction. It's kind of the structure kind of hangs out from the machine. So what we have is a little bit of resonance going on. So because primarily one-time RPM, right? Then my value here is roughly, let's say, 116 watts. And then my peak here is still going to be, in this case, 34 versus 33 watts. And that's just small variations. And you can see here's my 2-time and my 60 hertz. You can see right in there the peaks are separated just a little bit. 60 hertz does not show up in vibration. Instead, it's got its own peak. See what that value is. So that is 59 point, that's 3577. So 2-time from here, and you can see it also showing up here. So there's basically everything we saw before, and you can see that as we go out, the 3-time is there as well, and it shows up. It's also down in here. So they show up virtually exactly the same. One more thing to show, and then we'll end today's presentation. And the other thing I thought I'd show real quick is you notice the peaks are a little sharper now and everything else. Similar values. That's because what I did is I changed this now to a Hamming window or Ham window. So in any case, you have the same type of windows and other things with vibration for both. And again, when I switch both over, because remember, kilowatts or power spectrum is going to now be just one time. There's not going to be any sidebands. We eliminate the line frequencies, the carrier frequency, as part of that. So if I take a look at this end here, and I'm looking at everything in dB, the running speed for vibration is my highest peak. So that's going to show up as my 0 dB, and everything's going to be related to that. So I can see that my noise floor changes based upon which peak is higher, and my kilowatt analysis remains similar. Not clear on what these peaks are, but you can see there's virtually no peak down here. It's very, very small, and it could be almost the noise floor. And then at line frequency, you can see the peaks off to one side. It's a double peak here. So let's take a look now at one more thing. I'm going to take a look at current again. And we'll go ahead and pause. And here again, just to kind of show the same type of thing, you can see that my 30 hertz peak is showing up at either side of the line frequency. So this is current signature and this is vibration in dB. Okay, so my highest peak is here, almost here, and then as I go along, I can see similar peaks lining up between current signature and vibration analysis in decibels, in dB. If I want to change this one last time, let's go ahead and change these to linear, so we're actually looking at current and vibration. Okay, so after switching again, this is the horizontal reading. After switching, here's my current in amps. So this would be about the running speed current, and very, very tiny peaks on either side at 1 time RPM. This would be 0.176 amps. So basically, you never use linear to actually analyze electrical signature analysis. If you do that, it's not proportional. It becomes an issue. You can't relate it, and it's load dependent. So if I want to trend a particular peak in current, everything in the system has to be identical. All impedances. I can't turn on a light switch. None of that. And then I have to do all my other comparisons. When I change it over to dB, it eliminates all that and allows me to have something relative to my peak. Now, if I look here again, there's my peaks in inches per second, and then I can do those as my comparison here. You can see that value is very low, and this one's still high. So drive end low, opposite drive end higher on both parts. Now, again, you can see that I can really do some relationship between electrical signature and vibration analysis. So I always say a good ESA person usually has a background in vibration, let alone understanding the equipment that they're analyzing. That's crucial. Running around trying to do this all by textbook is never, especially if you're designing something, is never a good idea. You end up with, textbook and reality never meet. So we've run into a number of instances where we've been called out to go take a look at something saying ESA didn't work because of this, and we go out and we find out some person's developed ESA. They had no idea what they were actually talking about. Like 1 time RPM would be 1 time RPM off the nameplate, not 1 time RPM off of the varying load or the fact that it's on a VFD, that kind of thing. So let's go ahead now and conclude. So as I mentioned before, I showed you some variations of this, both in DMOD, which will match up very, very closely to vibration. So that would be my lower high frequency spectrum, et cetera, et cetera. Now, one of the nice things about this work that we're doing now is we've gotten some requests, quite a few actually, about being able to include vibration in empath ESA devices, and you can order them now. We made it official now, so I still have to put the marketing together. Been a little busy. We've got a large number of installations going on, as well as some conferences that are coming up. So so there is a version of the empath data collector that'll allow for vibration. That way you can use one instrument to take mechanical data on other pieces of equipment, let alone the ESA and vibration on your electric machines and driven equipment. The software is the same. The built-in data analysis is still there. So if you have an existing empath, guess what? It's an upgrade. So you would be able to have the cards added to your device, and it's just a matter of turning on 2 buttons within the software, and poof, there you are. So in any case, thank you very much. Sorry, this one is a little bit shorter, and all the pauses in between. Those were primarily to let me hack and cough up a lung a little bit. So with that, I will see you next week, and we will talk next week about what came about in the wind conference, the Wind Operations and Maintenance Conference that we're doing this week. We're flying out there tomorrow. and we are going to be having a little bit of fun. So we will see you then.